Okay, so we've just gone over the key to the exam, and today we're going to introduce the HEC-1 model. And in fact, let's work in the same location, this Grapevine Branch watershed. I think the reason why this particular location sticks in my mind is there was a news story a few years ago about a bunch of kids. I think they were at like gymnastics practice, and there was flooding in that location, and they kind of got trapped in the building for a few hours. I don't know if they were there for a birthday party or like for gymnastics practice, but they were stuck in the building because of flooding. And so, this is just one of several watersheds in the Huntington area that have had prominent news stories related to flood-related issues. So what we're going to do is I'm just throw it all out, start from scratch. So I'm not going to use that file that I just created, but I'm going to pause for a minute, and I'd like you to delineate the watershed at Bogis. So let's go to maps.google.com. Sometimes it helps to toggle back and forth between like the Google map of a location and then the WMS topographic map and street view and so on. So feel free, like when you're trying to locate the outlet, if I give you an address, you can use Google Maps to see where on the map is that spot. So here's Bogis. Let's delineate the watershed and also calculate the curve number. So that's where I'll start. That's where I'll break in. Like I'll pause and let you delineate the watershed again on your own, but then we'll go through the process of calculating the curve number together. Now keep in mind, since we're going to calculate the curve number, when you download the data, don't just get the elevation data. When you do that initial download data from web, you should get the elevation data, the land use data, and the soil type. And then that's what we'll have to use as the underlying prerequisites in order to calculate the curve number. You'll also need that table that I gave you before. Remember the curve number table.txt? We'll use that as well. But for now, just delineate the watershed. Now, something that I did, you know when you were downloading the elevation data and asked you what resolution that you wanted, it probably said 15, right? That was the suggested resolution, 15 meters. I said 7.5 meters, just so that I could illustrate that depending on how fine or how coarse your elevation model is, these lines will become relatively more smooth versus less pixelated and blocky. Like if you zoom in on one of the edges, you can see that the size of these pixels is smaller because I did the 7.5 meter elevation threshold. So that means, it doesn't mean 7.5 meter vertical elevation differences. It means each point which the elevation is defined for is 7.5 meters away from the point adjacent to it. So this is like a pixel map. And so, I mean, it didn't take that much longer for it to run Topaz or download the data. So, you know, you get maybe a little bit more precision if you have that higher level of point density by having a smaller point size. Okay, so we've downloaded the elevation data. I've got, here is the land cover database. So if we turn on the color of that map, what is it, that color-coded map? Surprised it's not showing up here. Maybe it's behind the street map. Anyways, I've downloaded the land cover database. There it is. I've got the soil data under the GIS, and it's County 11. Our watershed's entirety in County 11. So I can delete this County 99 data that it went and downloaded. And then the process we go through to calculate the curve number, remember, is we have to create a new coverage. So right-click on the word coverage, new coverage, and it is a soil type coverage that we're going to create. Okay, and then now that's just a layer that we're going to copy the applicable soil data into once we've joined the data table. You know, in the past, you used to be able to calculate curve number without creating a soil type coverage. And then that feature went away. I wonder if maybe they've re-enabled it for version 11.2. Maybe just to test that out, I'm going to go into the hydrologic modeling module. Don't follow down the same path in case it doesn't work. By the way, save your work frequently, right? But let me just see here if now I can go directly from the GIS data to calculating the curve number, or if we do have to create that new soil type coverage. So in the hydrologic modeling module, you used to go into the calculator, compute GIS attributes, and so instead of using the soil type coverage, like right now I have a soil coverage, but there's nothing in it because I haven't joined the data or copied the polygons into the soil coverage yet. But you can use GIS layers. And so I'm indicating that I want it to look at the shape tile. Now I may need to actually join the data first though, so let me do that. So I'm going to right click on this shape file and join NRCS. Okay, fill blank values. I guess C to be conservative for the blank values. Okay, now back to the calculator. So I'm going to compute GIS attributes, and so instead of the coverage, I'll use the GIS layers. And so I'm going to use the shape file, hydrologic soil group. It already knows that that's what it should look to for the soil group field. And then I have to import that text file table where it specifies the curve numbers. And then OK. No, it's not working. There's some way for it to work. I don't know. Land use. Oh, wait. Land use. No. That's from the, it's in a coverage. So the land use is in that TIFF file. Well, anyways, we'll go it the old-fashioned way, which was to copy the soil data into the coverage. So I'm glad you didn't crash your computer trying to do that. So let me turn off the elevation contours for now, and I'm going to turn off the land cover and turn on the soil shapes and select the ones. I could select all of them and copy all of the polygons into the soil type coverage, but I might as well just limit it only to the ones that actually need to be there. So in the GIS module is where I'll get this cursor that allows me to select shapes. So just make sure that you've got all of the shapes selected which are inside of the watershed boundary. So some of them are going to be excluded. So my soil coverage won't have every polygon in Cabell County. It'll just have the polygons that run through my watershed. So they're selected. I've already previously joined NRCS data, and now what I'm going to do is mapping shapes to feature objects. This soil shape file is going to go into the soil type coverage, and it knows to map the hide group characterization into the SCS soil type and finish. All right, so now I can turn off the shape file, and then the soil type coverage has all of the polygons that I need to calculate the curve number. So now I can go into the calculator, which is in the hydrologic modeling module, calculator, compute GIS attributes, and so it's going to be the soil type coverage and then use the grid, and the grid that we have is the National Land Cover Database from 2011. Browse to the file that has the land use key. So it's the curve numbers for a certain land use type. And then it calculates for a moment. It'll pop up the option for me to display a text file which has the summary. And this particular watershed has a curve number of 66. So that's even less than the last one. Last time we calculated the curve number, I think it was in the neighborhood of 68. That was the watershed over on Wildcat by the mall. This watershed has more type A soils, which brings the average down. Now we need this curve number because the model we're learning today is similar in a way to TR55. So in the tutorials that you put together as a homework assignment, remember you went through and you created a workflow for yourself that used the rational method, national stream flow statistics, and TR55. And why is TR55 the most accurate of those three? What is it that makes it the most accurate? Anybody remember why is TR55 better than rational method or national stream flow statistics? National stream flow statistics has the entirety of the western part of West Virginia in one region, and it only uses a single variable to determine the runoff. It uses the area. So what it's doing essentially is it's assuming that all of the areas in the western part of the state have the same precipitation, and they don't. That's not a good accurate estimate assumption. If we go to Precipitation Data Frequency Server, what we'll see is that there are little variations in precipitation depths from place to place. And so TR55 is superior because it uses locally applicable precipitation data, and it's better than rational method because it used curve numbers instead of C values. And curve numbers are calculated based on actual soil data, based on actual land use, rather than just estimated based on rules of thumb. So TR55 is great, but what we did is we assumed the type 2 rainfall distribution based on some depth. And HEC-1 gives you a little bit more resolution, which is useful when you're creating subbasins, like when you're breaking your watershed up into more sections. Like right now, our watershed is 960 acres. What we could do is we could break it up into smaller pieces, and the more pieces you break it up into, the more accurate your model has the potential to be. Because the water is going to be flowing in different ways in different parts of the watershed. Like the water flows from the ridge line over the land, but then once the water gets into a stream, it's flowing much more quickly through the stream in terms of velocity than it did over the land. So one of the advantages of HEC-1 is you can break watersheds up into subbasins, and it handles that effectively, but it also handles time steps pretty effectively. So did everybody calculate the curve number? Does anybody need help with the curve number before we move on to HEC-1 modeling? So I think we're still in the hydrologic modeling module. And over here on the left, where you get to choose your model, remember in the past what we've done is NSS, rational, and TR55. So select HEC-1 if it's not already selected by default. And then double click on that brown icon for the watershed. It's under the annotations right now, but double click and it brings up this window, which is where we're going to define the input parameters that go into a HEC-1 model. The first thing, let's just go through each of these cards, as they're called, one by one. And by the way, this is kind of where you see how old some of this computerized watershed modeling is. It was originally developed in, I think, an old programming language called Fortran, and I'm not sure if that's still the case. I think it's probably been translated into some other language, but it retains some of the original variable definitions from those early days, where these cards are assigned variables. For example, the basin area has a variable assignment BA. We're basically assembling an input file. It's just a text file that WMS is assembling for us that's going to be read by the HEC-1 model. It's kind of like a processor. So WMS helps us to create a text file that's going to be read by the processor, and then WMS helps us to read the output of that, which is the hydrograph. So here's our basin area in terms of square miles, and so it's always good to do a reasonableness check. So we know this watershed, what was it, 960 acres? And if a square mile is 640 acres square, if a square mile is 640 acres, then yeah, it makes sense that we've got about 1.5 square miles for this. We can leave these other parameters blank, but I will point out that you could put base flow in. If you knew that there's a particular stream that always has a certain amount of water in it because of maybe groundwater emergence into the creek. So you could put in a base flow of 20 CFS or something. If we don't characterize some base flow, then what we're going to get in the hydrograph is just the response from the storm that we put in. So we don't actually need to tell it anything for basin data. It's already calculated the area, and just by default, it's assigned it a name. Output control is another thing that there's really nothing we need to do here. This is WMS handling in the background some of the parameters that people would spend days and even weeks putting a HEC-1 input file together before they actually ran their job. And it's doing all of that automatically for us. The first thing that we actually do care about is precipitation, because we want to know what's the runoff from this watershed, but we haven't told it what kind of a storm yet. So we have to define the precipitation, and if you click on that precipitation, it gives you a few different options here. Like you could calculate what is the runoff during the probable maximum precipitation. Probable maximum precipitation is the kind of simulation that they run when they're trying to test whether a dam is likely to fail. Like they're assuming that like 3 storms come in from different directions, and it's basically clouds from ground level up to 40,000 feet, and all of the clouds are simultaneously raining. So probable maximum precipitation is kind of like end of the world event. And so that's not the simulation we want to do. It's not PMP. Basin average is typically how I'll define the precipitation. You could, though, define certain locations in the watershed that have gauges, and so then you could calculate how much precipitation exists in the watershed by going through and inputting the depth of precipitation and then like calculating a weighted average. So you remember the isohydral, the Thiessen method, the aerial average. So it has some built-in tools for that. But this is a relatively small watershed, so we can just assume that everywhere in here has a certain amount of depth. And so how much? Well, we can get the precipitation data from the web. If you click that, then it's going to access the NOAA Atlas 14. That's the precipitation data frequency server. So let's look at what is the runoff for the 10-year storm. So change it from 50-year to 10-year, and then when you click Get Data, it's using the latitude and longitude to go and obtain the precipitation data. The average precipitation depth is 3.63 inches. So the 10-year storm, which has a duration of 24 hours, has a depth of 3.63. And when you click OK, then it pastes that value in here to the depth. So we know the depth of the precipitation, but we don't know the temporal distribution. Do you remember that word, temporal distribution? It's just over a 24-hour period, what does the curve look like for when the rainfall is actually occurring? Time, depth, and what type storms do we have in West Virginia? Type 2, right. So a type 2 storm starts off small, has high intensity, then it tapers off again. It has kind of an S-shaped curve. So if you define series, then select under selected curve, scroll down to type 2 24-hour. And then what it's calculating for us over here is for a depth of 3.63 inches, how much of that precipitation is going to be assigned to what time. So it's got the relative fraction for certain times, and then when I click OK, it's copied all that precipitation data down into here. Like this is a little summary of the input file WMS is assembling for us for the simulation that's about to be run. Okay, so we define the precipitation loss method, click there, and you'll notice it's already copied over the curve number that we calculated before. So you have a variety of different ways to account for the ratio of infiltration to runoff. And by far the simplest approach, I think, is the SCS curve number, because we're using the NRCS method to say if you've got a certain curve number, then how much infiltration is there versus how much runoff is there. But there are some other methods that are available that we won't get into. Maybe you'll recognize green amped, because we've talked about that before. But let's do the curve number method. So we've got the calculated curve number from before. And then last thing that we have to define here is the unit hydrograph method. So that is, we got to tell it the time of concentration. And so click on the unit hydrograph method, and it doesn't know the lag time yet. And so we're going to calculate the lag time from the basin data. Compute parameters, basin data. So click on that, and then we have seen this window before where we can select, for example, the SCS method for calculating the lag time, which uses the watershed length, the curve number, the slope. So if you click OK, it already input all of these values that it knows based on the elevation data and the curve number, and then it calculates the lag time. So that's going to relate the delay from when it rains to when we start seeing a response in the watershed. Okay, so OK there. And we don't need to define anything about snow melt. We're just going to assume that the response we see doesn't have to do with base flow or snow melt. It's just precipitation causing runoff. This column on the right side where it says routing, there's basins and then there's also streams. And we're going to do our first simulation just with a single basin and not account for the delay in travel time due to streams. But these cards are how you could define the length of a stream, the width, Manning's N, and calculate how long it takes for water to flow through the stream itself. But we've just defined precipitation, loss method, unit hydrograph method, and now we're okay to go. So click on Done, and then under HEC-1, look under Job Control. Right now, by default, it's going to break our analysis up into 15-minute steps, and there's going to be 100 steps that it does. So let's just change that from, leave it at 15 minutes, but the number of hydrograph ordinates, change that to 200, just to make sure that we get the entire storm represented, and click OK. Now we can run the simulation. So HEC-1, run simulation, and it wants to know where it should save the file that it creates. You just do the default for now, just whatever it suggests, OK. Make sure though that it's not in some like deeply buried network drive. It should be like in your C drive and pretty close to the root. All right, so normal end of HEC-1. When I close that, it's going to show me a little hydrograph icon on the screen. And if I double click, then I can open up that hydrograph, and this is the stream response. We're going to have a peak runoff of 335 CFS. It knows the time to peak. Now this is assuming the type 2 storm, where it begins raining right at midnight, so to speak, at the beginning of the day. But the important thing here is it's calculated both the peak runoff, the volume of the runoff, and we could put in other precipitation depths in there, like the 25-year storm, the 50-year storm, and kind of look at what do the peak flow rates look like for those different storms. So HEC-1 is generally regarded as even more accurate than TR-55, and the way that you make it more accurate is by breaking your watershed up into subbasins. And so that's what we'll do when we get together on Friday, is I'll give you basically a location, and I'm going to step aside, stop talking, and ask you to delineate, calculate the curve number for the watershed, and then we'll go through the process of creating subbasins together. So that's it for today. I'll see you on Friday.